Thanks everybody for sticking around. And yeah, as Gordon mentioned, Michelle was supposed to give this talk, but she got waylaid in Taipei by bad weather, and so um, you have to forgive me if I'm a little unfamiliar and have to do some reading during this presentation. I'm going to be talking about some aspects of a climate change vulnerability assessment that we've been working on. I want to acknowledge the co-authors of the talk. Obviously, there's Michelle Reynolds, Crystal Kraus, and we are at the USGS Pacific Island Ecosystems Research Center in Volcano. We're also working with Paul Berkowitz, Kurt Storlazzi, and Jamie Carter. So there were sort of three primary objectives when the study began. The first was to identify habitat vulnerability in the northwestern Hawaiian Islands to climate change impacts. The second was to identify species-specific vulnerability, and then to evaluate Hawaiian bird sensitivity to climate change impacts in the northwestern Hawaiian Islands. But when this project began in late 2009, found out there's still no high-resolution elevation grids for the islands of Papahanaumokuakea. So sort of the initial part of this project was to acquire and develop those elevation models. So to sort of start, just wanted to let you guys know about three products that may help with climate change action planning. The first is a USGS open file report that sort of in press now, and we expect it to be out later this month or in September. And there's two chapters to that report. The first has new topography data for all of the low-lying islands of the northwestern Hawaiian Islands. And that includes species and distribution, some downscaled climate change projections, and inundation models. And then the second chapter of that report incorporates dynamic wave-driven inundation predictions for just for Laysan Island. The next report is trading off short-term and long-term risk, minimizing the threat of Laysan duck extinction, and that's the product of a structured decision-making workshop and is available online. And then this paper came out recently in Conservation Biology and focuses on threats in French frigate shoals, which has some of the best seabird data for all of the northwestern Hawaiian Islands, and looks at population dynamic effects from climate change impacts. So just some of the basic methods for the work. The first step was we acquired airborne LiDAR data to develop high-resolution digital elevation models for the low-lying islands. Data were collected in July of 2010. From these, we created high-resolution digital elevation models. We analyzed weather data for Laysan Island and Tern Island of French frigate shoals. And then we modeled passive inundation, which is also referred to often as bathtub models for four scenarios of sea level rise. So 0.5, 1.0, 1.5, and 2 meters of sea level rise. And so that sort of incorporates some of the uncertainty in sea level rise predictions over time. We also did land cover and habitat classification from satellite imagery, looked at inundation and habitat change, and then, as I mentioned, did a wave-driven inundation model for Laysan Island. Some of the details for the LiDAR data collection, because for collecting LiDAR data over land, the plane needs to fly at less than 800 feet. We had a timed data collection for when there was fewest seabirds in the area, so there'd be less potential flight hazards, and all of the LiDAR flights were based from Midway Atoll. On this slide is also an example of a topographic map and elevation histogram of Laysan Island that was derived from the LiDAR data collected. And so we developed these types of detailed elevation figures for each of the low-lying islands, and these will be available in the report that's coming out later this summer. This is just an example of some of the high-resolution imagery. I mean, this is East Island and French Frigate Shoals, and in this, hopefully you guys can see it, you can do a turtle count from this imagery. It's just very high resolution, and so it's great for evaluating vegetation and coastline. This is just another image, and this shows sort of how they can be mosaic together, and how we can use them for land cover analysis. We also, because some of the LiDAR data took a long time to receive, we also did some evaluations from satellite imagery, so from Photosat and WorldView 2, and we use some of these images for habitat classification as well. And these are slightly lower resolution than the LiDAR. So on to some results. With the elevation models, we evaluated the inundation from passive sea level rise for each of the 20 islands. And this example from Sand Island shows that at 1 meter sea level rise, only about 2% of the island is expected to be inundated. But if you jump to 2 meters of sea level rise, almost 40% of the island is predicted to be inundated. So there's sort of this threshold that's crossed between 1.5 and 2 meters of sea level rise, where a large area of the island becomes inundated. But when we look at Lisiansky, which is one of the larger islands in the northwestern Hawaiian Islands and has a mean elevation of about 3.8 meters, this island is predicted to have relatively small impact from sea level rise, with only about 2% lost at 1 meter and about 5% lost with 2 meters of sea level rise. But when you look at the small islands, it's a different story. And so this is southeast island of Pearl and Hermes Atoll, and on your guys' left is sort of you can see how we did our vegetation mapping. So we use sort of coarse classifications of vegetation, and then on the right is the inundation predictions. And so at Southeast Island, with just 1 meter of sea level rise, 58% of the land area is expected to be lost, but 97% is expected to be lost at 2 meters of sea level rise. And bird species distributions vary throughout the islands. And Southeast Island is small, but it's one of only 2 islands in the entire chain that the Laysan finch reside on. So the loss of this, although small island, could have a huge impact on a particular species. Overall, across the islands, if you include all the low-lying islands, with 1 meter sea level rise, we predicted about 4% of the land area would be lost. But at 2 meters sea level rise across the islands, we predicted about 26% would be inundated. And again, that's with the passive inundation model. But because we know passive inundation models will probably underestimate sea level rise vulnerability because it doesn't include waves. So it doesn't include the wave inundation of the area. We collaborated with Fish and Wildlife Service and a USGS oceanographer to include wave run-up. We did this at Laysan. And so at Laysan, we include the passive inundation plus the wave-driven inundation. And we found that wave-driven inundation increases with sea level rise because reef crests, wave-driven inundation increases with sea level rise since the reef crest attenuates less wave energy with higher sea levels. Thus, passive models underestimate inundation during periods of high wave energy by greater and greater amounts as sea level rise increases. Problem is, in order to develop these more complex models, detailed bathymetry data are needed, and those are only available at Midway Atoll. And at Laysan, we had to create the bathymetry in GIS using about 8 different sources, including old navigation maps. Okay, so these figures are probably very hard for you guys to see, but on the On the right is, I'm sorry, on your guys' left is just the straight passive inundation model, and then on the right includes the wave inundation. And so with passive inundation at Laysan Island with 2 meters of sea level rise, only about 15.5 hectares is predicted to be inundated. So that's only about 5% of the habitat. But when you incorporate waves, the wave-driven inundation, as much as 17% of the island is expected to be inundated. And for those of you that are familiar with Laysan at all, there's large dunes on the south coast there, and once sea level rise, that the wave inundation breaches those dunes, and so you'll have seawater in the interior of the island. So another thing that we considered was groundwater rise. No hydrological studies have been done on Laysan. However, evidence suggests some percolation of seawater into the lake is likely, since the lake has not dried out in the past 7,000 years. If percolation does occur, lake levels may rise at the same rate as sea levels. So in which case inundation would occur in low-lying areas adjacent to the interior lake there. So we evaluated habitat loss with that scenario as well. And this is a little bit of a busy slide with some small images. But what these images are showing is the distribution of 9 avian species on a composite inundation pattern as the background. And so this allowed us to visualize how specific species distribution patterns relate to various inundation scenarios. And it might be hard to pick out these. We have a species like black-footed albatross that's more located around the coast, so the dark area, and you can see they would be largely impacted by wave-driven inundation, but wouldn't be largely impacted by rising groundwater. But when you get a species like Laysan albatross that are distributed more uniformly around the island, they're impacted by both groundwater rise and wave inundation. And then sort of a very different species would be the sooty tern on the right there, which moves around every year and nests somewhere else, and their nesting distribution is largely in between the areas of wave-driven impacts and the areas of groundwater rise. So they're less likely to be vulnerable to sea level rise impacts. And so the habitat overlap maps give us a spatial image of vulnerability, but there's an important temporal component when looking at storm impacts. Inundation by storms will have the greatest impact on species that breed during the period of high wave energy. So we used hindcast buoy data from near Laysan to explore this phenology, and so the green and yellow parts of the lower part of the figure shows when birds that are breeding, and so when that breeding period overlaps the period of high wave height and wind speed, that shows a period of vulnerability for the species. And so peak breeding of blackfoot and Laysan albatrosses, bone-and petrels, and Tristram storm petrels occur during this period of highest wave energy. And the 2 petrel species also nest in underground burrows, which make them particularly vulnerable to inundation from water inundation. The grayback tern is somewhat unique in that amongst the terns, in that it nests during the winter storm season and has a pretty restricted breeding period, and so it was also considered vulnerable. We did sort of a more thorough vulnerability analysis for we did 17 of the 21 species of seabirds that nest in the northwestern Hawaiian Islands, and we looked at some broad characteristics of the species and evaluated them for the entire region. And so there was the sort of focus of the vulnerability index was to predict the relative vulnerability of wildlife in the northwestern Hawaiian Islands to added threats from climate change at the breeding colonies. And so I'm just going to go through this really quickly. We identified 9 vulnerability factors and organized those into 3 groups that were broadly characterized as exposure to negative climate change impacts, their adaptive capacity, and the population status and global distribution. And then we ranked those on a scale of 1 to 3. I don't really have time to go into details of all the 9 of the factors, but for a group like adaptive capacity, just to give you an example, birds that are able to lay multiple clutches or relay if their nest is lost, and maybe are more readily able to nest in different locations on the island, were ranked as less vulnerable, while those that are species that are highly phylopatric and are not able to relay if their egg is lost were considered were ranked as more vulnerable. So when we synthesized the results, we found that in general, albatrosses and petrels were more vulnerable to climate change impacts because they have a lower adaptive capacity, more limited global distributions, and many populations are already considered threatened by other causes. There's some variability among the species with similar life history characteristics because of seasonal differences in breeding. So the time of year and their overlap with storm impacts. Overall, our results highlighted 5 species as most vulnerable to threats of the colony: blackfoot and lace-sand albatross, bone-and petrel, Tristram storm petrel, and grayback tern. And so finally, we also considered land birds, and there's 2 endemic land birds that are restricted only to the low-lying northwestern Hawaiian Islands. It's the lace-sand duck and lace-sand finch, and they were also considered highly vulnerable. And so overall, the climate change scenarios and potential sea level rise impacts presented here emphasize the need for early climate change adaptation and mitigation planning, especially for the vulnerable species with breeding distributions and ranges restricted to the low-lying northwestern Hawaiian Islands. And I think I will end there. So if there's any questions.